If you haven't done so yet, please pause the video and try to answer the question on your own before listening on. Our first step in solving this question is to draw in the currents. And when we draw in those currents, we have to make sure that we do it for each branch of the circuit. So let's take a look at how we could do that. We'll head on over to the first battery that's marked E1 right here. And typically when you draw current, you draw it so that it projects away from the larger terminal of the battery. You can see there's a large terminal here and then a smaller terminal here. It's common to label the large terminal with a positive sign and the smaller terminal with a negative sign. And again, current typically, though not always, typically exits from the positive terminal of the battery. And so what we can do is project an arrow that's heading in this direction. And since they've labeled this E1, we can call the current I1. Similarly, if we come over here to this battery, it's marked E3. The larger terminal is the positive terminal, the smaller one is negative. We project the current away from the positive terminal typically, so we'll draw an arrow going in this direction, and we can label that current I3. And then we come to this branch of the circuit where we have the E2 battery, and it might be tempting, based on what we've said so far, to project the current away again from the positive terminal. But the problem with that is that then you'll notice that all three currents, I1, I3, and then what we'll call I2, would all be heading towards this junction marked C. And we can't have all the currents moving towards a junction. We have to have at least one moving away from a junction. So in fact, we'll erase this current arrow and point it in the opposite direction. Now, choosing the direction for the currents is an arbitrary choice in the beginning. What I mean by that is, if it turns out that we chose the wrong directions, we can actually go back and fix that later in the calculation. So for now, we don't have to really sweat whether these are the correct directions or not. We're just making our best guess. So now, after drawing the currents for each branch, what we're going to do next is apply the Kirchhoff's junction rule. And that rule states that the total current that's flowing into a junction is going to equal the total current that's flowing out of a junction. And if we come over here to junction C, we can see that current I1 is moving into that junction. Current I3 also is moving into that junction. So we could add those two currents together on the left-hand side of this equation. And then we can see that current 2 is flowing out of that junction because it's projecting away downward from that junction. So we would put that on the right-hand side. And so this actually becomes the first of three equations that we're going to need. And for now, we'll just kind of slide it out of the way and hold on to it. The third step is to use the Kirchhoff's loop rule. And when we do that, we can pick an arbitrary starting point, so perhaps right here. And we're going to move our way around one loop of the circuit. So for example, we can move from A to B, C, F, and then back to A. So sometimes it's helpful to draw a little arrow in to show the direction of that loop. And as we move around this loop right here, we're going to keep track of the potential changes, the so-called delta V values. So let's start doing that together here. We can begin to move around our loop, and then when we come to this battery, we move from a negative terminal to a positive terminal, and that battery is labeled 70 volts. And so we would have a positive 70 volt potential change. It's positive because we're moving from the lower terminal to the higher terminal, essentially. So we continue moving around the loop, and then we're going to move this way. We encounter this battery, but now we're moving in the opposite direction. We're going from the positive terminal down to the negative terminal. That's 60 volts, but it's going to be a negative potential change, so we would do a minus 60 volts here. We continue our way around the loop. We're flowing with the current. That's marked I2, you'll notice. And then we encounter this resistor. Now we know that for resistors, the potential change is equal to the resistance times the current. And so we can see we have a resistance here of 3 kiloohms and a current that's given by I2. Now because we're flowing with the current, we have to make sure that that potential change is negative. Anytime you flow with current, your potential change through a resistor is negative. So we would do a minus sign and then the resistance of 3 kiloohms multiplied by the current I2. We'll keep in mind later that this value of 3 is actually in kiloohms, not in ohms, but for simplicity, we'll just call it 3 for now. We continue moving around the loop, and we encounter this resistor right here. So once again, we're going to have a potential change equal to the resistance times the current. Now, in this case, the current that we'll use is not I2 anymore, it's I1. And if that's hard to see, just try to imagine the tail here of I1 kind of extending backwards, like so. You could even put another little arrowhead on it. Remember that that's I1. And we're moving with the direction of I1. So that is, again, a negative potential change. And so we're going to have a minus sign of the resistance of 2 kilo ohms multiplied by the current that's flowing through that resistor, which again is I1. And then we finish our movement through the loop and we return to where we had started. Now, anytime you return to where you start in the loop rule, you can set the total potential change equal to 0. And then we can also clean this equation up a little bit by subtracting the 70 and the 60 to make 10. And so this becomes the second of 3 equations that we're going to need, so we'll set this one aside as well. Now, we will need a third equation, and the reason we need a third equation is because we have 3 variables. You'll see in these equations we have I1, I3, and I2. So when you have 3 variables, you'll need 3 equations in order to solve. We can actually apply the loop rule again, but we'll just make sure to choose a different loop. So let's start right here. Let's move in a direction that would be in this manner here until we return to where we had started. We'll keep track of the potential changes. So here we go. We're going to move from the negative to the positive terminal. That's a positive potential change equal to 80 volts. So we'll have positive 80. Then we'll move along and flow through this resistor. We're moving with the current marked I3, so it's going to be a minus sign. And then we'll multiply the resistance of 4 kilo ohms by the current I3. And then we'll continue through the loop and we go from a positive terminal to the negative terminal of this battery. That's a negative potential change equal to 60 volts. So we'll have a minus 60. And then we'll flow through this resistor right here. We're moving with the current marked I2. And so again, that's a negative potential change. It will be 3 kilo ohms times the current of I2. And then finally we return to where we had started, so we could set this equal to 0. We'll simplify by combining the 80 and the minus 60. And then this becomes the third out of the 3 equations that we'll need. So here are the 3 equations, and now it transitions from a physics problem to a sort of algebra problem. Usually what you want to do in this case is leave the first equation alone, so we're not going to modify this one. And we'll notice that both the second and the third equation both contain I2. And what that essentially means is that we're going to solve each of the equations for the other variable. So we're going to try to isolate I1 in the second equation, and then later we're going to try to isolate I3. That's going to be our strategy. So in the second equation, in order to isolate I1, we'll go ahead and add the 2I1 over to the right-hand side, and we can come down here and show that work. And then we'll divide each term of this equation by 2. Okay, and so we've successfully isolated I1. We're going to hold on to that result. And now to this blue-colored equation, we're again trying to solve for I3. So why don't we go ahead and add the 4I3 over to the right-hand side. And then we'll divide each term by 4. And we've successfully isolated I3. Now the reason that this is a neat strategy is that we can take the expression for I3 as well as the expression for I1 and plug them into this equation up here. So the expression for I3, the 5 minus 0.75 I2, we're going to plug that in for I3 up here, and then the 5 minus 1.5 I2, we're going to plug that in for I1 up here. Maybe we'll come over here to show that work. And what we'll notice is that we have an equation that contains only one variable, I2. So why don't we gather those I2 variables, we'll add the 0.75 I2 over to the other side, as well as the 1.5 I2. The 5 plus 5 can be combined to make 10. And then we can divide by 3.25. And when we do that, we get roughly 3.08 is equal to I2. Now, as for the unit, usually the unit of current is in amps. But because we had been using kilo ohms for our resistance rather than just ohms, it turns out that these currents are now in milliamps. And so this is the correct answer for I2. Now we can go in and plug in I2 right here to solve for I3, and then plug it in right here to solve for I1. And so when we plug in to solve for I3, we get roughly 2.69 milliamps. And then I1 turns out to be approximately 0.385 milliamps. And so this, or these answers, would be correct for part A of the question. Now on to part B, which asks for the potential difference between points C and F. What that means is we want to begin at C and move our way to point F. And while we do that, we'll keep track of the potential changes. And whenever we move from point C to point F, or any two similar points, the notation would be VF minus VC, because that would be the final potential minus the initial potential. Again, we'll keep track of potential changes. So same rules as before. Moving from positive to negative terminals means a negative 60 volts potential change. And then we're moving through the resistor in the direction of I2, so that will be a minus sign. And then we'll have to multiply the resistance of 3 kiloohms by the current I2, which we had determined to be 3.08 milliamps. And when we crunch this down, we should get negative 69.2 volts. And that will turn out to be the potential difference between points C and A. If the question only wants the magnitude of the potential difference, then we would technically have to take the absolute value. And in that case, the magnitude of the potential difference would be positive 69.2 volts. And finally, the fact that moving from C to F represented a negative potential change, that means that the potential at point C is higher than the potential at point F.